in static fluids, something super interesting happens when you submerge an object, so typically some kind of a solid, in a fluid. Now, if you're thinking of fluids, of course, this is not just water, okay? So this is any fluid, so it's any gas or plasma, and not necessarily water in terms of liquid, so any liquid will do. So if you take an object, okay, and you start to submerge it in, you will experience that the actual object, it's almost like the fluid itself is pushing up, okay, to prevent you from kind of pushing something down. Now, of course, from Newton's laws, you know, for every action there's a reaction, okay, so it might kind of remind you that if you're going to displace the fluid, okay, so something might be happening. So let's try to explain this in this video, and it relates back to Archimedes' principle. Now, this is, you know, centuries back, so this has been quite a while back, okay, and it's a very interesting concept, okay, with regards to fluids. So now Archimedes basically said the following. So this is not necessarily his wording, this is more like my wording, but definitely his principle. I have nothing to do with it. Okay, so it's the buoyant force, okay, that is present on a submerged object in a fluid is equivalent. So it is the same to the weight of the fluid that would be displaced by the object, right? So let's break this thing down, and I'm going to try to explain to you what exactly this means. Now, first of all, let's try to talk about this buoyant force, right? So what the heck is this buoyant force? If you take any object, now it's much easier to be able to just describe it in terms of kind of a rectangular prism as we have here, but this doesn't have to be a rectangular prism. It can be any object. And you start to submerge it in a fluid. So let's imagine that we have a fluid. Now, again, it doesn't have to be water, but it could be, right? So let's say we have submerged it in a fluid. So this is the top of the fluid that we have, and then this object has gotten submerged, all right? So that's what we have in there. Now, when we do that, we are aware of one very important thing. We know that there is pressure as you go deeper and deeper, right? So if you're at the surface, there's really just atmospheric pressure, right? And then as you get in, and I'm just going to talk about the gauge pressure here. So as you get in, right, so it's 0 at the surface, and then as you get in, the pressure increases, right, with the depth of the actual fluid. You can put up a link up above there if you've forgotten that. So now at any single depth, okay, or height away from the actual surface, we know that the pressure that is present is the density of the fluid multiplied by the gravity and then the height, where the height is the depth, okay? So the height from whatever object or whatever place you're talking about, okay, to the top. So if this is the case, then we have kind of two things happening here. At any single point, there is pressure, okay, which is acting on this object. Now, this object is basically six-sided. Now, however, okay, so the pressure which you are feeling kind of on the horizontal sides, okay, so this right here, okay, and then this right there, okay, so you know that there is pressure which is pushing up against here, you know, there's pressure horizontal which is putting up against this wall and then the back wall as well. So there's certainly pressures all over at every single point, right? So pressure is everywhere present, okay, on this, from the bottom, okay, from the sides and so on. Now, the pressures on the sides, right, because of the fact that the pressures are identical at the same depth, these will actually cancel off, right? So the left and the right, okay, so these guys will cancel each other off, okay? So this one will be gone, okay? The ones on the back and the front, okay, again, these are just horizontal sides, so these ones will also all cancel each other off. So really what you have is you really just have kind of two kind of pressures, okay, and as a result, two forces that are going to be present. There's going to be one on top, okay, and then there's going to be one at the bottom. Now, these two will not cancel each other off. The sides cancel each other off because they're at the same depth. So no matter where you are at the object, there's an equal, okay, one which is on the other side, okay, from the actual object as well. So they're at the same depth, so these will cancel. But the ones from the top and the bottom, they're not at the same depth, because this object has a volume, right? So it's not just a flat kind of surface. Even if it was a flat surface, there would still be some little thickness there. So because of the fact that there are different depths, then we have different pressures, okay, that are acting. So I'm going to call this, you know, pressure up on top, and then you have a pressure at the bottom, right? So these are the pressures that we have. So I'll refer this to pressure B, okay, and I'll refer this to pressure T. Now, what that pressure is, it depends on the depth, okay, that you have this object submerged. So, you know, you would have, I guess, two heights, okay? So from the top, okay, you would have a height all the way to the up to the surface. I'm going to call this HT, okay, for top. And then from the bottom, okay, so this is going to be a little bit longer, and this would have been H kind of B for the bottom. And therefore, as a result, you would have that the pressure up on top is going to be equal to the density that you have of the actual fluid you're discussing, okay, times the gravity, times the actual height. So this is going to be HT, right? So that is the pressure. At the bottom, you have the same thing. The density and the gravity do not change, but you do have that the depth or the height to the top of the surface is different, right? So this is what we would have. Now, from both of these, okay, so as we would take these out, so I'm going to just take this, kind of duplicate it, put it here on the side, and I'm going to take this, okay, and duplicate it and put it on the other side over here. Now, we can certainly figure out what the forces are that are present, right? So there's going to be some forces that are present in here. Now, there is, you know, if this was not submerged in a fluid at all, if it was just kind of, you know, standing in a vacuum, we know that we have a weight, right? The weight is going to be pulling this object down. Now, the question is, outside of this weight, which is pulling it down, are there any other forces that are present when you put this object in a fluid? And the answer is yes, right? Because if there's pressure on top and you have pressure at the bottom, and these two pressures are not identical, so they don't cancel each other off. So therefore, there must be some force which is present up on top, pushing it down, and then there's also a force which is pushing it up, coming from those pressures. So if you were thinking about this, then, you know, so you have this force which is at the top, and then there is a force which is at the bottom, and they're not really equal to each other. Okay, so what are these particular forces? So when you can kind of go back in here and say, well, hold on a second. Well, we do know, right? So if you take this, that pressure in general, so what it is equal to, it is the force that is present. So that would be the force up on top divided by whatever surface area that you have, right? And then the surface area here, it would have been the surface area which is present up on top on that object. So that would have been my area. Now, because I have a rectangular prism, right, so I also have an area at the bottom, right? So in this case, it's going to be the same area that I have. And therefore, you know, so on the right-hand side, I can say that this is equivalent to the force at the bottom, okay, that I have, divided by the actual area. Now, just so that it doesn't cause confusion, I'm actually not going to use B kind of moving forward. I'm going to put BOT, okay, so bottom. And you'll see that the reason for that, why, in just a moment. So you can, wherever I have put kind of B, let me just put BOT for the bottom, and I'll explain, you know, why I'm actually putting that in just a second. So that's BOT right there. Okay, so we have these forces at the top and we have forces at the bottom. And now if you would isolate, okay, or solve for that FB and FT, okay, or F bottom, okay, and F top. So what you would have is, so right here, this from this, if I wanted to isolate for that, I would multiply both sides by this A that I have in there. And what I would find is that the force up on top is equal to the density times the gravity times the H, the T, okay, and then I would have kind of this A right there. All right, so this is what I would have. All right, okay, so that's basically, okay, the force which is coming down from all the fluid, okay, up above, right? Up above it. So that's what you would have there. Now, on the other side, so this right here, so my force at the bottom would be equal to, so again, so this would have been my density, my G, okay, my H, and this is BOT, okay, I'll write that, and then multiplied by A, because I would have been multiplying both. So far they look very much the same, and the only difference really is, right, the height or the depth that you have been submerged from the top to the bottom. So those are the two forces. Now, one is acting, okay, up, and the other one is acting down. Now, the one which is at the bottom is going to be greater because that height, okay, to the surface is bigger, right? So really, if you wanted to see, you're going to find that the force, if we would draw kind of a schematic in here, and we would find that the force at the bottom minus the force at the top, T, right? That would have been the overall force acting upwards due to the pressure of the fluid. And this right here, so if you would write this entire thing out, so notice they both are dependent on density, so that's that. They're both dependent on gravity, okay, so that's that. Okay, so then now they have the area. In this case, because it's a rectangular prison, it's the same. Okay, and really what I'm doing is I'm factoring this thing out, and this would just be H, okay, at the bottom minus H, okay, up on top. All right, so this is what you would have in here, so T right there, and that's the overall force that is present. Well, this force is the buoyant force that we are referring to. So the buoyant force, it's the force that is pushing the objects upward just because of the fact that you're suspending them in a fluid. So if you immerse them in a fluid, doesn't matter if it's a fraction or the entire thing, you're going to have, okay, this extra force, okay, that is present there. And that force, so now, okay, I can formally say this is the buoyant force, and I guess I'll designate the little b now, okay, or the capital B for the buoyant force, okay, so, and it doesn't confuse you with the bottom force. So it's not equal to the bottom force. It is actually the force between the bottom and the top, right? And this is going to be a non-zero force. It's always going to be something if you're dealing with a fluid that has some particular density, right? So as long as you have density, okay, of this, obviously gravity is always going to be pulling it down, okay, as you have there, you have some surface area, and as soon as you create, okay, so there's a difference between the bottom and the top, all of a sudden you have this buoyant force, right? So that is present. Now, this buoyant force that you have, that is exactly what Archimedes was referring to. So what he's saying is that, oh, you know, you have all this wonderful math that you can try to do it. The problem is, now notice, I did it on a rectangular shape. Now, sometimes people do a cylinder. It doesn't matter what you have, right? But the reality is you can take any object. I mean, if I would take this pencil and try to submerge it, it would be difficult for me to figure out exactly what the top area is, what the bottom area is. I mean, it's curved. So Archimedes has figured out through kind of experimentation and said, oh, you know what, this force, sure, we can calculate it. Not that he thought about calculating it, but we can find it in a very different way. And what he said was, you can find this force in a very, very easy way. So this force can be found by simply, okay, knowing the fact that whatever object you have, if you place it and submerge it in, it is going to be equal. So it is equivalent to the weight, because please remember, the weight is a force, of the actual fluid that you have displaced by the object. Right? So that's what happens there. So in this scenario, if you're looking at this, kind of let me remove this out of the way for just a moment. So if you take this, right, and I'm going to now duplicate it. And let's say I'm going to submerge it in. So here's a tank, and I've placed it inside of a tank. So as you know, if you submerge it back in, now all of a sudden, by submerging it into the actual fluid, you have displaced the fluid itself, because the space that it occupied now is occupied by the actual object. And when you displace that particular fluid, okay, then what happens is that this right here, okay, will be, it has a volume, right, attached to that displacement. So how much volume did you displace, right? So this is a volume that gets displaced by the fluid. Now, if we know the dimensions, we of course can find that. Now, if you know this, right, and you can calculate how much of the fluid you've displaced, then you can find out what the weight of the fluid is. Now, you might say, how would I do that? Well, please remember that the weight, so the force coming from the weight, okay, so that particular force is nothing else but the mass multiplied by the gravity, right? So whatever mass this is, okay, and multiplied by gravity, you can get what the weight is. But here, we're thinking about the actual fluid itself. So this is for the fluid. How much fluid has been displaced? And in order to do that, you can tie this in to density because of this fact, that you know that the density of whatever fluid you are dealing with is just simply equal to the mass times whatever volume it occupies. So hold on a second. This M right here, you can find by knowing what the density of that fluid is, multiplying it by the volume that has been displaced by the object, and then multiplying it by G. And now you know exactly. So here, this, because this M, okay, you can just substitute this right here in there. So that's the density of the fluid multiplied by the volume. So that's the volume that you've displaced of that object. And then if you multiply by gravity, so now you know what the weight is. And this weight of the fluid that has been displaced, what Archimedes says, this is the same thing as the buoyant force you're trying to find. So you can find it in two ways. You can actually find the buoyant force by doing the calculations, knowing the differences, kind of thinking about the pressures and then densities of those fluids. Or you can say, okay, how much volume has been displaced by placing this object inside of the fluid? And if I know that, okay, so if I know that, how much volume it has displaced, well, I know G, and I know what fluid I'm talking about, so I can take its density, and then I can multiply those, and I can find out what the weight of that fluid that was displaced. And that is exactly the same force that's going to be pushing up, okay? So that this thing, wants to get pushed upwards. And I'm sure you've experienced this. If you've taken anything, right, and tried to submerge it, especially if, if it's, even if it's something bigger, okay, like a ball, and you're trying to submerge it even in water, you'll see that it takes a lot. There's a lot of force, okay, that's preventing you from pushing it down because you're trying to displace that much water or whatever fluid it might be, and that particular force is being pushed upwards. Let's try that in an example so that you can see how this works. So in general, okay, Archimedes, through his actual principle, stated that the buoyant force, which is pushing objects upwards in a fluid, is the exact same thing as if you took the object, okay, and you put it in the fluid, and you know what volume that was. So whatever you've displaced, what weight does that have? And these two things are identical to each other. Okay, so here is an example just to kind of end this video up. So let's imagine that we have a soccer ball. So here's a soccer ball right there, right? So we want to be able to submerge this in. So the soccer ball, let's say, has a radius of 11 centimeters, okay? And it has been fully submerged in water, right? Now, what buoyant force is present on the ball? Okay, so this is something that we would want to be able to find out. Now, it's submerged in water, so we have to kind of think back, right? So what's the density of water? Well, the density of water at approximately 4 degrees Celsius, okay, is 1.00 times 10 to the 3 kilograms per meter cubed, or in other words, right? So if you were thinking about this is just simply 1,000 kilograms per meter cubed, right? So this is what we have, or 1 gram per centimeters cubed, right? So you can kind of think back of density. I can put up a link up above there if you want to think about densities, okay, of various items. So that's the density, okay, of water. All right, great. Now this particular ball, so what is the buoyant force? So you would want to know, okay, how much force would be trying to push this ball upwards. Now, please remember that's mostly filled up with air. Sure, maybe you've kind of compressed it in, okay, so it's nice and firm, but it's still mostly air. So it would be very difficult for us to try to submerge it. So now this, you know, it's 11 centimeters in terms of its radius. This is kind of the regular ball that they play around, right, so that they kick around. So how would I do this? So I have the density of water. Well, so if I want to find that, it would be difficult for me to, you know, find areas and so on. It's, you know, as you can see it, right, we don't even have, okay, so if we were thinking about kind of from the top to the bottom, you know, we can think about the diameter, sure, you know, from top to bottom, but the area itself that we have from the top and to the bottom, right, so it's spherical. So it's much easier for us to say, okay, if you want to know what the buoyant force is, just use Archimedes' principle. And what he said was, okay, well, you know, if you submerge this ball entirely in water, right, so how much water would it displace, right? So that's the question. So this, you know, how much water does this displace? Well, it displaces, okay, the total volume. Now, the volume that we have for a sphere is 4/3, and this is pi r cubed. So you may or may not remember that, right? So that is kind of the volume for a, you know, a spherical shaped object. So now we have everything here within. So now notice it's 11 centimeters. So this is 4/3. This is pi 11 centimeters. This is going to be cubed. Now I'm keeping it in centimeters because, you know, I can certainly do the density in centimeters as well if I wanted to. Okay, or I can change it back to meters if I wanted to, so that's up to us, right? So whatever is convenient for you. Now, I guess because we're doing the forces, we're going to need kilograms anyways, so maybe, you know, I can certainly go back, okay, and then change this. So the 11 centimeters is just 0.11 meter, okay, cubed. So now, what is that volume? All right, so let's do that. So it's 4 divided by 3, and that is going to be multiplied by pi, and then that's multiplied by 0.11, and this is going to be cubed. So it's going to be small because it's in meters cubed, so that's fine. So I'm going to just write it out. So this is 5.5752, you know, 797. I'm going to just keep it on my calculator there. So that's that times 10 to the 1, 2, and 3. So -3 meters cubed. So it seems rather small in comparison to a meter cubed. So that's the volume that would have been displaced by the ball. So that's great. So now I have that volume. So now how do I actually find out what the weight of the water would be, okay, within that? So that is, again, so this would have been the density of water multiplied by, this is going to be multiplied by the volume itself and the gravity. This is going to be times gravity, okay, and then times the volume. Now we have the volume right here. We know what gravity is. So gravity is 9.8 meters per second squared. And this right here, so if you keep it all with respect to kilograms and meters, right, then that way you're going to get the force in newtons. So this is just 1,000 kilograms per meter cubed. So now we're going to take our answer right there. We're going to multiply now by, so 9.8 multiply by 1,000. Okay, and we have it exactly. So this is, you know, 54.6377, you know, newtons, and that is, okay, the weight of the fluid that would have been displaced. And this is the same thing as saying this is the buoyant force that would be pushing, okay, or trying to push this ball upwards. Now, if you want to round it, you certainly can round it. Okay, you can round to whatever it is that you like. So let's round it just to 2. Okay, so this would have been our answer there. So that's what we would have, okay, for this particular example. Now, if you think back, right, so now for this, the actual buoyant force is present regardless if you submerge something entirely, okay, or not, right? So this is, if it's fully submerged. Now in part B, okay, something interesting is asked, because it's asking us, what is the buoyant force if the ball has been submerged halfway? So instead of submerging it all the way, what if we submerge it this much? Well, you're still then displacing water, right? You would only displace half of the ball's water, so the volume would have been half. So that would mean that, we would take our answer, so whatever that was, so in this case it was, I think, 54, so 54.63 and so on. So this, you would divide by 2 in here, because the volume that you've submerged this was by 2. So if you go back into the equation right here, okay, and you were thinking about this, then that volume right there, well, it's just volume divided by 2, because half of the ball is submerged. And then you would have your answer, which is about 27, right? So that's what it would have been, okay? And that's the newtons. And that is the force which is pushing upwards. And that's the Archimedes principle. So it's pretty cool that if you're capable of finding out what the volume is of an object, then you can do kind of wonderful things. Now, there's other applications, other ways to be able to figure these things out. And you might see that in other examples as well. But for this video, okay, I just wanted to present the principle to you and hopefully explain it in such a way that it should make sense to you. And now, you'll understand that when you do submerge anything in a fluid, you do feel that force pushing upwards, and that's the buoyant force. All right, thanks for watching. See you in a future video. Bye, everybody.